So for this video, we are looking at rectangular hyperbolas because we want to be able to expand our knowledge of types of graphs so that when we come across different types of graphs, we know exactly how to sketch them, what they look like, what they're representing. And after this video, you want to be able to identify the horizontal and vertical asymptotes, dialect, reflect, and just generally translate a hyperbola on a Cartesian plane, and sketch the graph of a given hyperbola. So if we consider the graph of y equals 1 over x, we could construct a table of values for that relationship, and it would look something like what we've just got on the screen here. So when x is 1, y is also 1 because you have 1 over 1. When x is 2, y is going to be 1 over 2. If x is a half, then it's going to be 1 over a half, which is effectively 2 over 1, and so on. If we were to plot all of these values, we would end up with a graph that looks like this here. So it's sort of a curved thing in the corners. This is what we call a rectangular hyperbola. So a rectangular hyperbola is literally just the graph of 1 over x with potential translations. If we think about our knowledge of domain and range and set notation, obviously if we have 1 over x, x cannot be 0 because we can't divide by 0. So our domain becomes that x is an element of all the real numbers excluding 0. Okay, and similarly for y, we cannot obtain a value of 0 with 1 over something. You can't divide 1 by something and end up with a result of 0. So our range, in the same way, y is an element of R except for 0. So what this is telling us is that because we have these values that our function can never take, and this is a function because if you do a vertical line test, it will always pass, that we have those values that x and y can never take. So if we think of that as x moves towards infinity, y is going to move ever closer to 0, but it can never actually exactly equal 0. So there's a little bit of notation around this. So saying that as x approaches infinity, the value of y approaches 0, but because we cannot have 1 over 0, we can't divide by 0, y can never reach 0. So this notation here and here is just saying that as x approaches infinity, y approaches 0, in this case from the positive side, because as x approaches infinity, y gets ever smaller, closer to 0, but it's coming from a positive number. And similarly, as x approaches negative infinity, y is going to approach 0 from the negative side. We would use the same notation to talk about the vertical asymptote, that as x is approaching 0, y approaches infinity, or as y approaches infinity, x is going to approach 0 from the positive side. It all means the same thing. It's just a way of describing the asymptote. So we can apply all of the knowledge that we have on transforming functions, so dilating, reflecting, translating them, and still apply it to a rectangular hyperbola. I'd recommend if you don't have this as sort of like a little cheat sheet somewhere, it would be a good idea to pause it and give yourself a little summary section, because these are sort of your basic recall of transformation rules. So effectively, we're saying that if we have the point xy and we move it h direction, or h units in the x direction, k units on the y-axis, we apply that to y equals f of x, we end up with y equals f of x minus h plus k. Since, in this case, f of x is 1 over x, what we end up with is, this is the important dot point here, that you end up with y equals your dilation factor of a over x minus h plus k. H is going to be your vertical asymptote, k is going to be your horizontal asymptote. So this example is asking us to sketch the graph of y equals 2 over x plus 1 minus 3. Now, this has not been reflected. It's still positive out here, which means we know that our function is going to look like that. It's going to be our regular rectangular hyperbola. We have a value of h here of -1, because if you remember, our form is that y equals a over x minus h plus k. So because we have x plus 1, our h is going to be -1, because we're subtracting the value of h. K is going to be -3, and our value of a in this case, our dilation factor, is going to be 2. So our horizontal asymptote is -1, our vertical asymptote is -3. What that tells us is that effectively our center point, if you like, so where the two asymptotes meet, is going to be at -1, and then I'm going to call that 1, 2, 3. So it's going to be about that point. We indicate asymptotes by using dotted lines, just to make it really clear on a sketch that that's where our asymptote is. Now, we know where our asymptotes are. Ideally, when you have a sketch, you want to know where your intercepts are going to be. So if we think that this would have a center at 0, 0, or just our basic sketch, we've effectively translated 1 to the left and 3 down. So it's going to be something like that. We're going to have an x and a y intercept here. So if we work out first our y-intercept, we just make x equal to 0. So we get y equals 2 over 0 plus 1 minus 3. So 2 minus 3 is -1. So we know we have a y-intercept at this point here at -1. And then our x-intercept, we make y equals 0. So we get 0 equals 2 over x plus 1 minus 3. So 3 is 2 over x plus 1. 3x plus 3 is going to give us 2. 3x equals -1. X equals -1 over 3. So that's going to be about there-ish, given that we've made this -1. So we can use those points and our asymptote to help us sketch that line. So it's going to go up like that. And then our opposite corner is effectively just going to be symmetrical to that. This was -1/3, that point there. So that's how we would sketch the graph, by working out those translations, x and y intercepts, and then plotting it all together on the graph. The second example asks us to sketch the graph of y equals -2 over x minus 1. Now, because our value of a is -2, that means we've had a reflection in the x-axis. Okay, so instead of looking like that, our hyperbola, we're going to reflect it in the x, so basically just swap the top and bottom, and it's going to have its parts of the function in those two quadrants of the Cartesian plane. Now, other than that, we've got a value of h of 1, we've got x minus h, and a value of k of 0. So our center point is at 1, 0. So there, which means that our asymptotes are going to be at 1 and just along the x-axis, so we don't have to draw that one in. Now, if we think about where everything is going to be, we're going to have one segment down here. It's never going to cross the y-axis down here, never going to cross the x-axis. The other one is going to be up here, so we are going to have a y-intercept. So we need to work that one out. So when x equals 0, we get y equals -2 over -1, which is just 2. So we know this point here, we're going to have a y-intercept. So from there, you can just use that to sketch your graph. You can see from this graph, it's effectively just the graph of y equals 2 over x, and then translate, so it's then reflected with the negative, and then translated 1 unit to the right on x. So it's just your standard hyperbola shifted over to the side.